Hello guys, welcome to ECE TechNest. On day 6 of the Verilog coding and digital design, we'll be learning data flow modeling, behavioral modeling and switch level modeling. In the last lecture, we learned about gate level modeling. Today we'll be starting with behavioral modeling. This is what has the highest level of abstraction and it focuses on what is the circuit doing rather than which gates to be used. It looks very similar to C programming. We use procedural blocks like always, initial. We also use if, else, case and for loops. The best example for this would be complex logic like ALU, state machines or controllers. ALU is generally designed using behavioral modeling. We will see this ALU design in our further lectures. For as of now, we'll learn with basic examples. For today, we'll be learning behavioral modeling using a 2:1 multiplexer. As you all know, based on the select line input, whatever is in your first input will go out as output and the second input will go only when there is select line is 1. That is, when you see here, I'm telling it always at A or B or S. It means whenever any of the one value changes in this and when S is equal to 1, your output Y is equal to A. Else output Y is equal to B. That means here it is telling I0 and I1. Your A stands for I0 and I1 is B. So whenever it is 1, output A will be given as input A will be given as output and input B will be given as output when S is equal to 0. In this style, we just tell the computer if S is 1, output A, otherwise output B. It's as simple as that. In data flow modeling, this level describes how data moves and transforms between registers. In this, we use continuous assignment. Here, we used to have procedural assignment inside an always block. But here, it's a simple continuous assignment. And this is used for combinational logic and simple equations. Let us see how it works. The same 2:1 multiplexer that we saw here can be written in this form without a procedural block, directly using a continuous assignment. We use assign Y is equal to A and S, B and OR. This is OR B and not of S. So what happens is when S is equal to 1 when S is equal to 1, A is the output, and when one of your S is equal to 0, B will be the output. The assign statement is continuous, meaning anytime A, B or S changes, Y is updated immediately. Switch level modeling. It has the lowest level of abstraction. Instead of gates, we use transistors, MOSFETs, switches. It is rarely used for complex digital design today, but it is very essential for custom CMOS cell design. We use keywords like PMOS, NMOS and CMOS. This is best for designing basic gates from scratch and specialized low power circuits. Let us see how this works. We have a CMOS inverter. To build an inverter, we connect a PMOS to the power source and an NMOS to the ground. This part of your circuit is PMOS and this part of your circuit is NMOS. Whenever the input is given, it goes to both the PMOS and the NMOS. Depending on what input you are giving, the output will be generated. This is a simple code. Let us see how the code is made. You have a module inverter. Your input is in and output is out. You need to define the supply. Supply 1 is always VDD. That means VDD is 1. Supply 0 is ground. Now we'll see how the syntax is written for switch level modeling. You have the primitive name. Primitive name is PMOS, NMOS, like that, and instance name. Instance name, if you want to know perfect meaning about it, it is nothing but how many times you are calling the PMOS. Again, if in this code, if I'm using PMOS, I'll be calling it as P2 because I've used it for the second time. It's the easy way of writing it. And always, as we spoke, output has to be mentioned first and then the other input sources. Here, we are talking about connecting the output to the VDD when input is low. That means output, then your VDD and your input. VDD and your input are input pins and out is your output pin. NMOS N1 out, ground and in, because ground is here another input. See, when input is equal to 0, since PMOS is an inverted gate, it pulls out the high. So the V out will be 1, and it is pulling out the node up to VDD, that is logic 1. So V out will be 1. In case Vn is 1, so the 1 goes here, and this circuit has 0. So this becomes an open circuit. So it is connected to the ground. Pulling the out node down to the ground, we'll get logic 0. The PMOS is off. That means the PMOS is open, and V out will be equal to 0. That is how inversion works. In comparison, if you want to write an inverter or a CMOS inverter using data flow style, we'll just be writing as assign output and a NOT gate inverted. Whatever your input is there, we'll invert it. In behavioral style, we'll write always at input, begin, output is not of in, end. This is how we'll write it in behavioral style. In today's lecture, we'll also be learning about a test bench. So many of you might be wondering what is a test bench. The main thing what we do in our test bench is we write out the number of possibilities, like for this input what might be the output, we'll test it. We give the most number of inputs and check for certain possibilities or outputs what the design might return. See, in here we have module my inverter, right? For this we are going to write test bench. Let us see how it is written. So we have an input register and wire is out. So we need to convert our inverter design to a test bench. So we use my inverter, DUT means design under test. This is your output and input. We take this because here you can see when I previously wrote my module my inverter, that is CMOS inverter design, I mentioned the name as my inverter. So again, when I want to connect it to the test bench, I'll write my inverter design under test out and in. So initial begin, I'll write the statement $monitor. This is for the output, how the output has to be shown in the terminal. And I'll give few set of inputs. When input is 0, set input to 0. Input is 1, it sets input to 1. This hashtag 10 is the time units. Like after 10 seconds or 10 milliseconds, the input will again change to 1. We'll see this in the waveform. And I finish it with $finish and an end module. I have done the execution using EDA Playground. I'll put the link to this below. You can go and work on the code there. Here what I am doing is I have written the same design code and the test bench code. I will run the code. So what happens is you can see whatever was my monitor screen, time is equal to 0, input is equal to 0, output is 1. So at 0, input is 0 and output is 1. And after 10 seconds or 10 milliseconds, when time is 10, input becomes 1. At that time, output is 0. So for an inverter, whatever was the maximum input conditions giving either 1 as input or 0 as input, I have verified it and I have got a perfect output. Let us verify the same using a test bench. See here, my input is 1 for the first 0 for the first 10 seconds. For that, I am getting output as 1. So my inversion is working. For the next 10 nanoseconds or milliseconds, see here my input is 1 and output for that is 0. So my inverter is working properly. For this design, I have made a test bench and I am getting the desired results. This is how we will go about in the further lectures using simple what you call executions in EDA Playground. If you have any doubts, feel free to put it in the comment section. Thank you.